All right, guys, anything else from the quiz? Okay. So you can make corrections, obviously. What are those corrections due? Day of the next test. When's test one corrections due? Day of the next test. What's the only thing not due the day of the next test? Homework corrections.
That's due the day of the final.
Which is cumulative. There you go. Finals cumulative. That's what the man is. Could you turn in quiz one corrections on the day of the final?
No.
Of course you could. Yeah. Could you get points for it? Of course you could. Just not anywhere near as much. But you could turn quiz one corrections in, day of the final. If you do enough of the corrections right, you could get a point or two depending on what your grade was. Does that make sense? Why do I let that happen? Finals cumulative. I want you to study whatever you can. Right. Okay. We finished that handout last time. You guys, I'll give you another minute or so to look that over. Let me know if you have any other questions from that quiz. Or maybe I'll give you a couple more seconds. You've already been looking at it. The stats for the quiz are up on the board. Very weird distribution. But, I mean, it kind of makes sense. It was you know it or you don't situation, yes? So it's very bimodal. What's going on here, yes? Pretty good pass rate, pretty good average, but I don't like that number. Okay. Well, you can improve your Latin life with corrections. And, I mean, again, if you left sections of chapter 3 where you didn't even do any of the homework, obviously you're not going to do as well. So it's almost good. The only good thing about doing poorly is if you can identify what it was that caused you to do poorly, because then you can change it. Okay. What really sucks is if you do poorly and you feel like you're doing everything, that sucks. That sucks for you, it sucks for me. So we can meet, we can try to figure out what's going on. You guys kind of with me? Yeah. As a teacher, that's the roughest situation, because I'm like, holy shit, it does look like you're doing everything. So then we got to figure out what's going on. Okay. Anything left over from the homework or anything before we get into our next thing here?
It's gonna sound like a silly question, but what section should we be on?
If you haven't started 4-1 homework yet, I don't understand you. So maybe you've been focusing on finishing chapter 3, but your primary focus should always be new homework, right? Unless there's a quiz coming and there's stuff on it you haven't done yet, then that's your focus, so, right? So last time we took a quiz, so since then your focus should be chapter 4, yes? Okay. So I'd say right now you should have done some out of 4-1 at least. Okay. Help from my friends. Yeah, here, come here. So I gotta orient myself. Yes. Aha. You know, real quick, just to let you guys know, I tried using like an iPad where I connected the computer wirelessly and I was walking around. My handwriting is even worse on the iPad. So I liked being able to walk around because I hate being over that stupid corner, but my God, I'm like, no. No. So I went back to this. So here I am, I'm over here still. So we did 4-1, 4-2. We developed the formulas. You've got the, so if I have this formula on my formula sheet, right? And you should. What is that the formula for, first off?
Population.
Population what? No.
Oh, variance.
Variance, cool. What column would I need to show up in a table so I can do what this formula needs me to do? So I'm going to be given x p of x.
And then you need
Eventually, what column do I need to
x
show up?
squared p of x.
yes, if I cover this, I need a bunch of those. So then I can add them up. Yes, does that make sense? I need to get you to the point where you got the formulas written down and they will tell you what you need to create. Yes?
Yeah.
I can't add stuff up until I get the stuff. I like it. So we did the whole handout, we did all that stuff. So if there's no specific questions from that, I'm going to get into 4.3. Okay. So last time I talked a little bit about this. Yeah, I'm gonna still do this. I think I gave this to you guys last time. The last study I've seen about this for Americans specifically, the probability somebody's left-handed is 11%. Very quick, because apparently I can't stop myself. Do you guys know back in the day they would try to strap somebody's left hand to their body and force them to use the right hand because they thought using the left hand was wrong. Some people even thought it meant sinister things. In fact, that's where the word sinister comes from. Do you guys know that?
No.
So that probability could be higher, but it's been literally tortured out of people in the past. So thankfully we stopped doing that. So what's the probability somebody's not left-handed?
99. Oh, 89.
80. If you know the probability of something, you know you automatically know the probability of not that thing, correct? So this holds somebody who's right-handed, somebody who's ambidextrous and wouldn't say they're left-handed, somebody who doesn't have both hands. This is everything else. Okay. So, bless you. Let me do this, because this is kind of clunky. Would you all agree if I'm, all right, what's going to happen in statistics is we're going to have something we're going to identify as a success. And a success could be finding a rabbit squirrel. That could be a success if that's what we're looking for. You with me?
Right.
Success does not mean happy thing. Success means what we're looking for. Now in this case, it's kind of neutral. If I'm looking for left-handed people, which one of those is the probability of success? 11%. So the letter we give to the probability of success is P. So P is 0.11. Does anyone have a clue what we call the probability of failure? What do you think that symbol is? I like it. Q. Math people, we like to do successive letters. What's the two important letters in algebra? X and Y. Yes. When we talk about vectors, it's U and V. All this kind of, we like successive letters. Let me stop for a minute. You guys with me? It's just notation, and you'll see why. It's going to make this. It's going to make formulating the formula easier, and it's going to make the formula itself easier to write. Instead of writing P of L, blah, 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 just write P. Can't like it. So, what I started doing last time at the very end of class was, what if I pick 5 people at random from America? Yes. Somehow I have the ability to do this. Yes, I can teleport, or I got a nice fast helicopter, whatever. I can get around real fast and get 5 people. We have assembled a team of 5. So if we pick 5 people, neato. Sorry, I would appreciate that for me. Stats class has become a video game. Pick 5 people now. Okay. If I pick 5 people, what is the probability that exactly one of them is left-handed?
No.
Nope.
Oh, you have to do the whole thing.
That would be if I picked one person. What's the probability that that person is left-handed? 11%. If I pick 2 people, why is the probability that exactly one of them, why would it be different? Because it could be either one. You guys with me? So the more people I pick, the higher probability I should get to get somebody, or it should be different probability, yes? Okay. Let me stop for a minute. The kind of probability you guys saw on the quiz and before this, I would say the probability the first one is left-handed and the other four aren't. Isn't that just like the problem I gave you on the quiz?
Yeah.
This is different. What's different about me just saying exactly one is left-handed? It could be the first person, or the second person, or the third person, yes. And what does or mean in probability? Add them all up. So if I find a probability of each of those and add them up, I get the probability of this. That's why the probability should be higher more than likely, because I'm increasing the chances because I'm letting any of them be left-handed. It's definitely going to be a higher probability than just the first person being left-handed. That's more specific. You maybe? So we're in the, let me tell you, right now we are in the process of developing a formula to do everything we're about to do quicker, yes? So we're gonna go through that. As you watch us do this, and as you do this with me, just keep reminding yourself, you're never gonna do exactly all the stuff I'm doing now. We're gonna kind of like get a shortcut. Okay. I love it. You would, Jeff. Okay. Can somebody give me one way? And remember, what am I calling the probability? So I've got 5 people, yes? I'm not gonna keep drawing those hangman spots. So what if the first person is left-handed? What letter do I want to put there?
P.
P. And then what would I put for the other 4 people?
See that?
See what? Oh, this? I'm sorry. Go ahead. What about the other 4? Q, 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 Q. And just to make sure you guys really understand, in English what's happening here is the first person is left-handed, and second person is not left-handed. Yes, and means multiply. Yes? So I got P times Q times Q times Q times Q. Or what? Or means add, yes?
Yeah.
So the first person is left-handed, or if the first person could be left-handed, or
Not left-handed.
the second person could be left-handed. Yes. What is it I'm looking for? I want exactly one person to be left-handed. So what must I include? I must include all the ways that can happen, yes? You with me? If I want to find somebody in here who's wearing glasses, can I just go, one chance? No, I must include every way I can get somebody that's glasses. You guys with me? Okay. So that's one way to do what it wants. Or I could do it this way, yes? And now you start to see the dance that P is going to take. Q, Q, P, Q, 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 P, Q, 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 P. Okay. See how it just propagates through? How many did I end up with? 5. Why does it make sense that there's 5 ways to have one left-handed person out of 5 people? Because it could be any of the 5 people. So of course it's 5. So this list is small. I can read it and I can see how many there are, correct? Algebraically, what is each of those? P times Q times Q times Q times Q. That's insane. How would I write each one of these in algebra? You can do it. What's Q times Q times Q times Q? Q to the 4th. I'm just going to write a lot just because everybody enjoys my writing. Yes, and then I add, and I get, what would I get then? What's PQ to the 4th plus PQ to the 4th plus PQ to the 4th? Please don't say 8. Please don't say. You can do it. What's X plus X? What does exponent mean? What does an exponent mean? What operation does an exponent mean? What operation is an exponent? Multiple, right? How would you figure out what 7 squared is? 7 times 7, yes. You guys all with me? Exponents mean multiply. which is why I put a fourth power on the q, because how many q's are multiplied? 4. Coefficients mean add. How many pq to the fourth do I have? Adding 5 of them. So I have 5 pq to the fourth. So what's the only time exponents will change? Because what operation are they based on? So what's the only time an exponent can change is if I am multiplying. Q to the fourth times q squared becomes q to the sixth. Is everybody, no?
Yeah.
I'm not currently teaching you exponents, but I sort of am. Okay. Well, this is very important, so a little side note. I'm going to do this. I'm going to take you through my lecture about exponents, because this is important. Once upon a time, there's a guy who was writing up a paper, a mathematician, and he had to write that 78 times in this paper. And by about the 13th time, he's like, screw this shit. I gotta come up with a way to communicate to everybody I have 5 x's adding. You with me? Can you imagine if we had to do 80 x's? X plus x plus x plus x plus x. You would very quickly go, is there a shortcut way to do this shit? Are you guys with me? Does that make sense just by itself?
Yeah.
Okay, good. This is the semi-drunk history of math, but it's pretty close to the actual kind of like idea. So this guy, or more likely a woman that a guy stole the idea from, because that's the real history of math. X plus x plus x plus x plus x. He said, let me put a 5 in front, and that will just tell everybody I have 5 of these things adding. So if I had 50 of the damn things, I could just put 50 X, yes? You guys with?
Yeah.
So a lot of learning math is just catching up with the shorthand shit that some old white guy in the past did or took credit for, yes? And we just have to catch up with that. You guys kind of with me?
Yeah.
Which is why math is hard, because they made stupid decisions sometimes. And we're like, well, that's dumb, but okay. Let me stop for a minute. So far, so good?
Yep.
So coefficients keep track of how many of that thing is added, which is why you need like terms to combine things.
Right.
Because you can't keep track of, if I say 1 chair plus 1 table, I don't have 2 table chairs. That doesn't make any sense. I have 1 chair and 1 table. Okay. So then across the world, there's this other guy doing this. And he just got word that this guy, he's like, I'm going to just call this 5x. And then he's like, oh shit, man. That guy, screw that guy. Screw that guy. He's like, I was about to say a 5 in front means multiply. You guys with me? He doesn't want to write that 78 times. So he's kind of come up with his own way to kind of write it quickly. Yes? And he gets word this guy is like, and again, this is not exactly what happened. A little dramatization, yes? Okay. So he's like, okay, shit, let me see. Maybe I can do this. That's weird. Maybe I can do, that just looks like division, yes? Maybe I'll do this. That doesn't look like anything else we've done. So now that means 5 of these multiplying. That's all freaking exponents is. That's it. You guys with me?
Yeah.
Okay. And so every property of powers comes from that definition. What do I do when I multiply x to the 5th times x to the 4th?
Oh, you add them?
Because I have 5 x's
I need you.
times another 4 x's is freaking 9 x's, yes?
Yeah, I get you.
Of course, what's the common mistake? Somebody would say this is x to the, what do you think people would say? X to the 20th, because their brain says I'm multiplying. Now here's where I'm going to really trip you up. In this, there is no 5. There is no spoon. There is no 5 in this. There is no 4 in this. Do you guys understand what I mean by that?
Yeah.
Because that's what the shit that represents, isn't it? Do you see a 5 here? Do you see a 4 here? And just collecting how many of these I have in a row. So if I got 5 and I tack 4, of course I got 9 in a row, yes? Okay. By the way, real quick, if you know this shit really well, just hang out. I want to make sure everybody's on the same page. How are we all feeling so far?
Very good.
Okay, good. So if I do x squared plus x squared, what part of that cannot change because I'm not using the correct operation for it? What are exponents based on? Multiplication. So it's the only time they'll change is when I am multiplying. Did these powers change?
Yeah.
Yes, the 5 and the 4 made 9. Because I was multiplying, which is the operation exponents are based on, yes? Am I doing the operation that exponents are based on? No, I'm doing the operation that coefficients are based on. So I have 1x squared plus another x squared. I have how many what's?
2x squared.
2x squares, yes? If I had x squared times x squared, that shit is x to the 4th. Okay. How are we doing? Okay. Is that okay? All right. What's up? Sort of? If it's not okay, let me know. Because we're going to use exponents quite a bit. Yes?
So why is it different for when it's adding?
Oh, okay. Let me ask you this. If I just see somebody write 7W, what does that represent? Yeah, and that represents W added to itself 7 times, yes? If you're in grade school and you need to do 7 times 4, what is the first way you do it before you've done much multiplication? You write a 4 7 times, yes? Because that's what 7 times 4 means. You with me? Okay, so if I have anything plus itself, for example, 3 times, how can I collect that together? M plus M plus M is how many M's? 3 M's. You with me? Would that change if it was A plus A plus A? Still 3 A's, yes? What if it was, I don't know, what was it, Araceli plus Araceli? What would that be? 2 Araceli. Yes? Did I spell your name right?
No.
Damn it.
So then the exponent just carries over.
So, real quick, I haven't even talking about exponents here, have I? Coefficients keep track of how many times the same thing is added. So, coming back to this, I have an x squared, and then I'm adding another x squared. So, how many x squares do I have now? 2x squares. See that? That's it. The 2 is just keeping track of how much shit I got. I got a bag. Somebody puts an x squared into it. Then somebody else adds an x squared to it. How many x squares do I have in my bag? 2 of the damn things. Yes? You can see, in fact, some of you guys earlier would have said the answer was x to the 4th. And you can look back and say, oh, young me, you had no idea. But there's logic there. But logic can be wrong, and that logic was wrong. And now do you see why this is right? Okay. So coming back to statistics. And by the way, I do not mind taking a moment to do this. Because I know some of us haven't taken math in a long time, or you took it recently and it didn't go great. I understand that. So please, dear God, feel free to ask me. It's up to me to determine if I have time to do it. Yes? So now does it make sense? If I'm adding PQ to the 4th plus PQ to the 4th, I just say to myself, how many of these do I have?
Right.
5. So I have 5 of these, yes? And why were they each PQ to the 4th? Because it's P times Q times Q times, and then Q times Q times Q is Q to the 4th. I have 4 Q's multiplying. So, what did P, now look at what we just got. I want you to see how I don't have to do all this stupid shit. Thank the gods, because can you imagine what if I said I pick 80 people? Yes, if I said I pick 80 people and I want exactly 1. How long would this list be?
A long.
80, all right, so do I want to do it this way? No, I did it this way just to show you where this comes from. So can somebody tell me why this bit, what power is on the P? 1, okay. Can somebody tell me, how does that piece of this expression relate to the problem we're answering? I want 1 success, correct?
Yeah.
Which means I have how many failures?
4.
4 failures, yes? And what is that? 5. What does this 5 come from? Don't say 1 plus 4, that's not why. Where'd the 5 come from?
How many different ways you can try?
Yes, the length of the list, yes? All the different ways you can do it, you with me?
Yeah.
Okay, let me stop. Now, let's go ahead and finish this up, because don't we know what P is? Don't we know the probability of a left-handed person? What's the probability of a left-handed person? I told you earlier. 11%, and I want one of those. And so what's probably of a not left-handed person?
E9.
And I want 4 of those. Can you guys plug that in your calculators? And if you don't have a calculator, maybe come get one. Come with me and you'll see a calculator doing stuff. Oh, neato.
It's got nothing on it, but
Oh, shit. Man. I was gonna do some unrelated stuff on my phone, though. Just look at Amazon and see what was going on. No, it's not one.
Sweet, thank you.
Okay. So can you guys all try to do this in your calculators? Whoa. So you can just literally put it in exactly the way we've written it. 5 times 0.11. You don't have to do 2 to the first. Is that cool?
Yeah.
Although you could, let's just do 2 to the first. Hit the arrow over key to come back down, yes? Unless you have an older calculator that doesn't do exponents like that. Are you guys all with me? And then keep going. Times 0.89 to the,
Four.
there's your to the button, 4th. Shaboom! 0.3451, I think, if I see that right.
Yeah.
Yes. What does that mean? Sorry, go ahead.
And then the student is also 4 decimal places?
Yes. Yes. Once we get to chapter 6, you will see what I've been getting you ready for with the 4 decimal place request. What does that mean?
34.51% chance
Of
of getting left-handed person.
getting one left-handed person out of any 5 you pick. So 34.51% of the time, I will get one left-handed person from a group of 5. Yes?
Yeah.
Can you say that again?
34.51% of the time, I will get one left-handed person out of a group of 5 I pick. So if I have 5 people coming to a little workshop I'm doing, and I have one left-handed desk available, 34.5% of the time, that'll be the correct number of desks for left-handed people. Does that make sense?
Yeah.
All right. So if you are left-handed, some rooms probably don't have enough left-handed chairs because it's just the probabilities. They're playing the probabilities. We're getting to the point where I think I talked about this already. Did I ask you guys who's ever been bumped from a plane? If you go to fly,
Yeah.
yes? They're playing the probabilities. They're like, almost certainly some people are not gonna show and we want a full plane, so we're gonna overbook it by a few. And in case somebody does, we can just give them some money because we're making stupid amounts of money, so screw it. Right, they don't say that out loud, but.
How'd you put it in the calculator again?
So, clear this. So you put 5 times 0.11, and you could put to the first if you want. When you do this in your calculator, Steven, does the, all right, let me make sure you're with me. 5 times 0.11, and then to the first. When you do that, does it go up?
Oh, I was doing it like second with the exponent.
No, yeah. Does it look like that?
No. It has to be on it.
And then you got your to the button, right?
Oh, so that's the to the button, okay.
And now see how I'm up though? If I write
Yeah.
anything else right now, it's gonna be in the power, so I have to hit the over arrow to come back down. Times 0.89 to the 4th power. Okay, so. Let's try a fresh situation. Just to try to develop a general formula for this. We kind of have the beginnings of the general formula, yes? So let's say I pick 66 people. And I want to find the probability that exactly, what, Jeff? 7 are left-handed. Let me see if I can get you guys to really get this. Does anyone want to make the list like we did? I love math, and I do not want to make that dumbass. Are you kidding me? I really need you. You have no idea. You have zero idea. So I'm going to ask you the thing that you don't have a clue about. How long do you think the list would be? So what I'm saying is, couldn't it be beep, 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 like the first 7, and then the rest are Q's? Or maybe the last 7, and the first ones are Q's. Or maybe the first one's a P, and the last 6 are P's. Or maybe the first 3 are P's, and the middle 2 are P's, and the last 2 are P's. You guys, you see what I mean? So you're just imagining 66 spots. Where can you put 7 P's? How long do you think that list is? Give me a guess. I got a guess of crazy. Just give me a guess. Huh?
240?
220. That's pretty good. No. Harold's is like this exactly what I was. 400?
Yeah.
Alright.
It's like 900.
Higher. Huh?
It's like 900.
900? Higher.
2,000.
2,000? Higher. Alright, let's find out. You want to know exactly what it is? So before I do this, does everybody get an idea? You know it's going to be a lot.
Yeah.
Well, however, if it's anything over 10, I really don't want to do it, do I? 10 is pushing it. I'm going to show you in a minute. So remind me, where did this number come from? How long the list is. Do we know how long the list is yet? No. So I'm going to leave that blank, yes? Yes?
Yeah.
Okay. P, how many successes do we want? We know that. How many successes do we want?
7.
7. So how many failures do I want? You can do it. How many people do I have?
66.
And I want 7 of these successes. So I want 59 failures. What must these two powers always add up to be? The total number. So whatever the situation I give you, they must add up to be the total number. Does that make sense? If I have 80 people and I break them up into 2 groups, whatever one group has, the other one's got to have the rest. Yes? Okay. So if I have 66 people and I put 7 people in one group, the other 59 have to go into the other group because the groups are mutually exclusive. Together they make the whole thing. Is that cool? You alright? Okay. So the only thing I'm missing, I can put that shit in the calculator, but that's not the formula, is it? I'm missing how long the list is. Yes?
Would you do like 66 to something? Like how many times?
Oh, no. So here we go. You ready?
That was just a hypothesis.
I understand. No. I appreciate guesses. Dear God, don't self-censor in terms of taking guesses as the math.
Okay.
That's not a bad guess. So, here's what we're going to do. This thing costs a lot of money, yes?
Yeah.
For whoever got it, you or whoever. Costs a lot of money. It better be able to freaking count. That's the least I would expect this dumb thing to do, yes?
Yeah.
And you are dumb. It's dumb. It's going to murder me tonight. What am I? You're dumb. Oh, man. All right. So there's a really cool... There's a little extra probability idea that we just don't have time to get into in this class, and they're called combinations and permutations. I don't know if anybody's ever heard of those. It's really kind of nifty. Combinations is what we're going to focus on. Combinations is the number of ways you can choose from a group. In fact, since it starts with the letter C, I often just call it choose. How many ways can you choose? Yes?
Right.
So if I have 30 people in the room, how many ways can I choose one person? 30 ways. Whereas how many ways can I choose 2 people?
60.
That's no.
Oh.
A lot more than that. And that's why the birthday paradox works, because there's more pairs than you can imagine. So, you ready? You ready? Everybody put 66 in. 66 is the total we have, yes?
Yes.
How many do I want to choose from that? 7. So I'm gonna go. I'm gonna hit the magic math button. Math. It should be like confetti on the screen or something. Math. I'm gonna do something related to probability, correct? See over here, probability? Which one do you think has to do with combination, with choosing? Yes, don't do National Public Radio, do choose.
Wait, where's that? NCR?
Yep. If anybody plays Fallout, it's not the New California Republic.
Aw.
66, choose. Now, real quick. Is everybody with me?
Yes.
Does anybody have, like, it says NCR here?
Yeah. Mine does.
You're fine.
Okay.
Yours just doesn't look like this. Who cares? Everybody else has this?
Yes.
Does everybody not have either of those? Is everybody with me? Choose how many again?
7.
7. Where's my cursor at the moment? It's down, isn't it? So if I wanted to put more shit in, I'd have to hit the over arrow. But actually, right now, I just want to do this. This will tell me the number of ways to choose 7 things from 66.
Okay, wait, pause. So.
I will.
Okay, sorry. Continue. Oh.
No, I said I would.
Sorry. Okay. As a space.
7.
I just put a 7 like that.
It's still the same as that one.
Yeah, 7. Yeah. Of course it is. It just looks different on the screen.
Oh, because.
Put a 7 now, because 66,
Yeah.
choose, that's what NCR means, 7, enter. Is
Okay.
everybody getting that number? What number is that?
77.86, which could be 88.
Careful. Comma, comma.
Oh.
778 million, 789,004. The list would be that freaking long. Do you understand?
That's crazy.
Do you understand?
Yeah.
That is.
Again, this is just another way that, so the G20, you can see now I was kind of like, but I'm not laughing at you because this is so not intuitive. It is so not intuitive, but if you just started to try to make the list, maybe it's the first 7, maybe it's the first 6, and that P goes marching through. Maybe it's the first 5, and those 2 go marching through. Maybe it's the first 4, and those 3 P's go marching through. I don't know if you guys are with me, but I'm thinking about making the list. And maybe when I march these 3 P's through, maybe they go over 1 and these 2 march through. Or maybe they go over 1 and this one goes marching through. And I am nowhere near done, am I, in making the damn list. So it might still not make sense. In fact, my calculator's like, oh God. It might still not make sense why it's that big. But it makes sense that it's big. Okay. So. And by the way, so what is this number? Where would it go?
In front.
I'll tell you where to put it, Jeff. Hey, I would put it right here. So I'm just going to put it right here. I'm going to put 66, choose 7. Now, real quick, I want you to see how silly easy it is to set this damn formula up. I got 66 people, choose 7 of them to succeed. So I have 7 successes and the rest are failures. Let me say that again. 66 people, choose 7 of them to be left-handed. 7 left-handers, 59 not left-handers. It's a sentence, right? It's an equation, but you can read it. So now real quick, you all agree with me that this piece is stupid big?
Yeah.
This piece, does anyone understand that will be stupid small? That will be dumb small. In fact, don't do this, I just want to see. Can this even handle it? Probably should tell it what to do, Jeff. To the 59th? Oh, it can. Does anyone know what that means?
10 zeros.
Yeah, move the decimal place 10 times, so there'd be 9 zeros in front of this, yes? Stupid small times stupid big becomes regular. So let's try it. Whenever I do a problem like this, I set up the formula and I put the whole damn thing in the calculator. 66, math, probability, choose 7. Now I better hit the over arrow if yours looks like this. If yours has the NCR showing up, you can just keep going. Hit the over arrow times 0.11 to the 7th, over arrow to come back down, times 0.89 to the 59th. Shabbat. So we have a 15.67% chance out of any group of 66 people to get exactly 7 left-handers. So as is customary in statistics, this is the one place you do this. We're going to develop the formula for what we just did after we just did it. So a formula, in general, really just captures a process. So the process exists, and then afterwards we write a formula so I can communicate to other people what the process is. Does that make any sense? A formula isn't given to us and then that establishes the process. There's a process and the formula tries to capture that. In algebra, sometimes it feels the other way around. Here is the formula given to us by the gods. You shall put shit into it. Yeah. So what is this formula? Can somebody remind me? In fact, I'm going to give us a few variables. We already know what this is. What would this be as a variable? P. What would this be? Q. Now, I need a few more variables. We already know what this is. What is always the total number of things?
Oh, no.
Total number of things.
Why?
No, the total number of things in statistics. What letter do we use for the number of things? N. Now, X will show up. What part of the problem could I have changed? I couldn't change the 11% because that's a known fact. And I'm leaving the 66 people. So what part could I have changed? The 7. I could have said probably exactly 6 of them, probably exactly 11 of them, couldn't I? That is the X. So the number of successes is X. Because that is the part that can change, and of course X is the variable, yes? So up here is X, yes? Don't worry, I'm gonna collect all this together into the actual formula. So here's the last part. Here's the part that looks the worst in the formula. How the shit did we get 59 again? We took this number minus this number, yes? In general, what is this again? N. In general, what's this again? So what goes up here? N minus X. Good. If I have N things and I take X of them, how many's left? N minus X. So what does the formula actually look like? Dear God, you crazy person. Here's what it'll say. N, choose X. P to the X, Q to the N minus X. And that is the probability of X successes. How many outcomes are possible in the kinds of problems we're doing? How many probabilities do I have? Which letters in there represent the probabilities that I'm given? So how many probabilities do I have? 2. So I have 2 situations, correct? So we call this a binomial probability. Bi meaning 2. So this is the binomial probability formula. Crazy shit. So if you roll a die, are there 2 outcomes? Of course there are. How about this? You ready? I roll a 5 or I roll not a 5. Okay, so as long as you have a situation where it makes sense to talk about this or not this, you can do binomial probability. Yes? You with me? Now if I roll a die, there are 6 outcomes, but how can I define events so there's 2? Of course, like I just did. I could say even or odd. I could say 1 or not 1. Yes? I love you guys so much. Yes? Yes?
Reading the first is one of them is the same one that's like N and A. Is that the same binomial formula?
Maybe. I would always forget this crazy book. Let's see. Do they use K instead of R like it is in the calculator?
So they
Instead of
use
X?
X equals K equals that equals K equals K.
Oh, okay.
Exclamation mark.
Hold on. I forget that they go deeper into things than we need to. Oh, okay. Here's what they're doing. Real quick. If I had 10 people and I want to choose 3 of them. Yes? How many groups of 3 people could I make?
10? Oh, no.
So how many, so I want to choose 3 people, yes?
Right.
How many choices do I have for the first person?
We will put the
3?
How many people do I have to choose from?
10.
Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, these 10 people here, yes? How many, and I want to choose 3 of them. How many choices do I have for the first person? How many choices do I have for the first person? I have 10 people, so I have 10 choices. Is that cool?
Yeah.
I have 10 things I could choose, yes?
Wait, oh, so 10 C 3.
So 10 choices for the first person, and now how many choices do I have for the second person? How many choices do I have for the second person? Not 10, because will I end up with 3 people if I choose the same person twice?
No, 9.
So I have 9 choices now, yes?
8.
8, crazy shit. And then you multiply that out and you get 720. Way more than you thought, yes? Way more than you thought. This is related to something called the factorial, and I'm just gonna point this out because I forget the book does this, but that's okay. It's not bad. They're supposed to. We just don't have time to get deep into this, but just so you know this exists. In fact, if you hit the math button in your calculator, do you see any punctuation?
Yeah.
Did I hit the right number? Punctuation. Oh, it'll be over in probability. Do you see punctuation?
Yeah.
Number 4! What that means, 4 factorial, for example, that's a factorial, means 4 times 3 times 2 times 1. That's what it's very single-minded. Whatever number I feed it, it just keeps multiplying until you get down to 1. Do you see how that would play into this kind of problem?
Yeah, because it keeps.
Especially if I chose 10 people, it would be 10 times 9 times 8 times 7, all the way down to 1, yes? Yeah. Okay, so you could play around with factorials, and what I'm about to say is very, 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 very not important. But does anyone agree with me that 10 times 9 times 8? That's not 10 factorial, is it? What is 10 times 9 times 8 missing that this guy has? 7 times 6 times 5. Isn't 7 times 6 times 5 times, isn't that 7 factorial?
Yeah.
So if I divide these two, then I get this, yes? What's 10 factorial? 10 times 9 times 8 times 7 times 6 times 5 times, isn't that 7 factorial? Divided by 7 factorial is 10 times 9 times 8. Now, what did I say about everything I'm saying right now?
Doesn't matter.
It does matter, but for us it's not really part of what we do. But just to show you, where is there?
Because I know I have a problem in the homework about that. That's all I know.
No, the problem in homework, you use the formulas we develop. You're not going to use the formulas they develop.
Oh.
Okay. Where do you even have that?
It's in section 413. Question 82.
Huh?
Question 82. Like
Question
the
82.
formula.
Oh, nope. It doesn't say anything here about factorial.
Those P equals X.
In fact, so, let me show you. So behind the scenes of this operation in the calculator are factorials. The calculator is doing a bunch of factorials to figure this out.
Ah.
So So this process takes the place of all these factorials. But can you see how the factorials play into
Yeah.
counting stuff? Okay, that's all I really need you to see. If this class was a full-fledged semester-long probability class, we'd get much deeper into counting theory, which would go into factorials. This class is a statistics class with a little bit of probability in it, so we don't. All right, let me stop for a minute. So, looking at the formula. If I know, I'm sorry, and choose X, we call it X. The calculator calls it R, but that's okay. If I know I'm dealing with a binomial problem, a binomial distribution, how do I know I'm dealing with a binomial distribution? There are only two possible outcomes, and they gave me the probability of each. They would be P and Q, yes?
Oh, gotcha.
If I know that I'm dealing with that, what do I need to get from the problem? N, X, P, Q. They have to tell me those things, and then I just throw them in, yes?
Did you realize that you're literally just reusing everything in X?
Yeah, and X, P, Q. That's all I need, and then I can throw it in there and get the answer, right?
Yeah.
So real quick, just to kind of look at 82. 82 is a little bit evil, not so evil, but they do give you information that doesn't matter. They sometimes do that. 82 wants to know eventually the probability, 82 here. Suppose that 1,000 babies from healthy baby nurseries were randomly surveyed. Find the probability that 2 babies were born deaf. So what does P mean in English? P, little p.
No success.
Probability of success is what it means in general. What's it mean for this problem? Finding a baby who is
Born deaf.
deaf, born deaf. You with me?
Yeah.
That's what they're looking for. That's what they call a success. Okay. Can anyone tell me? Can somebody point out the information they gave us that's unnecessary, that we don't need to know?
30? Oh.
Yeah, true. Because what kind of nursery are we looking at? Healthy baby nurseries. And what is this number here?
Intensive care?
Okay. You guys with me?
Yeah.
So just cross that shit out. Why'd they do that? Because that's real world. Real world doesn't tell you, this is the number you need. Real world says, numbers! And you go, that's the one I need, yes? So I have no problem with this kind of problem. Gave you extra shit, you have to identify, oh, that's extra shit. Yes?
Yeah.
Tell me again, what 4 things do you need to figure out? N, what's N? What's N in this problem?
30.
Nope.
1,000.
1,000. We have chosen 1,000 babies, yes? See somebody wandering, who are you? Oh, nobody. Doing a little study for class. Mr. Waller told me to call him. So N is 1,000, yes? What's P?
2. Oh.
Careful.
No.
2 would make no sense. 2 out of?
100.
No.
1,000.
1,000. 2 per 1,000, yes?
Yes.
That's the probability of being born deaf, which is what we're calling P, yes? P is 2 out of 1,000, which is 0.002. So what's Q?
Q. Whatever the rest is.
Yeah, 0.998. So you just have to do, so what's P plus Q always?
1.
1. 100%. Because whatever P doesn't have, Q does. So together they make everything, yes? So if P is 0.002, Q is 1 minus that, which is 0.998. What's X?
X is 2.
2. So once you figure out N, P, Q, X, you just gotta plug it in.
So 998 would be the.
0.998 would be Q.
Okay.
Yeah. Now, considering I don't want to do the homework problem for you, I do have a worksheet where we can work on identifying these things for ourselves.
Also, you would divide 1,000 by 2.
2 by 1,000, because it's 2 out of 1,000, yes. Oh, you trying to use the formula?
No, the phone is easy. Because
Where'd you get the formula from?
I got it from the
Okay, okay. I couldn't find it when I went through real quick, but now we have a better way to do it, don't we? Yeah. Okay. So guys, take a few minutes, see how much of this you can do. All this first problem here is me just kind of working an example problem out, showing you the keystrokes. Yes? By the way, I noticed some calculator I was using. I think most of you would have this. I saw a calculator where you had to do it like this, but I think most of you are going to do this, these keystrokes, the same keystrokes we did earlier. We have some weird updates for some calculators now. Total. Yeah. N is always the total number of people or things we're looking at. And get very much in the habit of when I ask you what P is, write the decimal. Yes?
Yeah.
You cannot put percentages into formulas. That will blow them the shit up. Percentages are things we made up. 15.2% means 0.152. That's the number. So like it just said, make it into a decimal, 0.152. Right, percent to decimal, you move the decimal back twice. Point 152. Yeah, move it twice back to make it smaller. Yep, you got it. Because we know it's got to be between 0 and 1. Right? Okay. And then Q you can do in the calculator, right?
Is P plus Q.
Is 1. So if you know 1, the other one you can get.
So wait, so it's like, am I adding,
Huh?
am I adding 1 to P? Am I adding, so like,
So
I have to find Q still?
if A plus B is 10 and B is 3, what's A?
A plus B is 10.
If B is 3, what's A?
7?
Yeah, 10 minus 3 is 7. So you do 1 minus the one you know, it's the other one.
So basically it would be.
1 minus 0.152.
Oh,
Yeah. If you know they make 1 together, then 1 minus one of them must be the other. Alright, now just to warn you guys, when you do number 2, you're gonna get 7, right? But it's not 7, it's, look at the end, it says -4, right? Times 10 to the -4, you gotta move the decimal back 4 places. Some of these probabilities can get small. Oh, and don't worry about, yeah, I always forget this thing. Just go up to number 3, we haven't talked about number 4 yet. So I'm just gonna catch up to you guys.
change this worksheet a little bit. Yeah. Okay. I was so focused on this part to get the keystrokes right. I changed this first problem. It used to be something else. So if you try this yourself, it should be 0.0539.
Oh, so that part is asking, and then we just put the formula together down there?
Alright, so part 1 is its own problem. If exactly 3 smoke, then X would be 3, right? Okay, so just in case you're kind of trying this out yourself, it should come out to be 0.0539. Yes?
Can you please check this?
Yeah, just a sec. Down here, totally different problem, but with the same situation, yes? Now I want 0 successes, not 3.
Right.
So 0, 44 choose none of them, so no successes, all of them are failures. In this case, I call them a success. Yeah, totally, we talked about that. So, here, what are you guys getting for this?
0, 0, 0, 7.
Yes! So what you're really getting is this, yes? And what does that mean again?
3 zeros and then the fourth place.
Move the decimal back 4 places, yes? So the shortcut is, I've always got to move it back once, so there's always going to be 1 less 0 than this in front of it.
Right.
So 0.0007, yes? There we go. Is that okay?
Yeah.
So I want to make sure you guys see that example with me, because that might happen sometimes in the homework, where you get a times 10. Please, dear God, don't say the probability is 7. That doesn't make any sense. A 707% chance. Okay. Does this sound familiar? Yeah. Same question, same probability, same idea. What would suck, now listen real quick. What would suck about trying to do that probability directly is, again, remind me, at least 1 means it could be the first guy, or the second guy, the third one, or the fourth, or the first 2, or the first 4, or the last 4, or the first 5, or the last 5, or the middle 5, and up to freaking 4. Screw that shit. What's the opposite of at least 1? None. So if I do 1 minus the probability of none, which is so silly better that better is not even the right word for it, because there's only 1 operation I have to do for none. In fact, we already did it. Yes? Whenever the question I'm asking you about a probability has more work than the opposite situation would, do the opposite situation and then do 1 minus that. Because how do 2 opposite probabilities relate? One is 1 minus the other one. If the probably it's going to rain today was 90%, when you woke up, what was the probability it wasn't going to rain?
10%.
10%, we know that. Yes?
So would you take your above 0, 0, 0, 7, and then would you do 1 minus that,
Yes.
or minus 1 from that?
If you minus 1 from that, you get a negative,
Okay.
which by itself doesn't make sense, but it's because this plus its opposite should make 1, so therefore 1 minus one of them is the other one. And this kind of makes sense. Even though it's a very low probability that one person smokes, if I picked a random group of 44, I feel like I should almost certainly pick somebody who smokes. Because I have so many chances to do it, yeah? You guys with me?
So it's 99.93%.
99.93% chance that at least one of them smokes. So if you have a group of 44 people coming to attend a talk, should you consider building in a break time and then possibly having a place where people can go smoke? Yes, because the probably at least 1 out of those 44 people smoke is pretty damn high. So, yeah, okay. Just to keep people happy so they don't kind of like revolt against you. Okay, now, I always forget this. But I want to do one more problem with this same number stuff. How would I do the probability of exactly, you can do it, it doesn't matter, exactly 11. How would I set that up?
So you do 44
Yeah, I got 44 people.
to C
Choose
11
11.
times
Success, how many of those do I want?
11.
So it's kind of nice that it's a little repetitive, yes?
Right.
Choose 11 from 44 to be successes, so I have 11 successes, and how many failures?
33.
33. Is that okay? I really, really want you guys to see how the formula is silly. It actually goes right with the physical situation. 44 people, pick 11 of them. 11 of them do this, the rest do that. And then if I plug it in, I get this. Oh, 333. Okay, how are we doing so far? Okay, this is kind of nice. This is one of the formulas that's like very, very in your face about how you can read it.
Makes sense.
That's my favorite phrase. Okay, so let me talk about the rest of this. Whenever I do this example, I always pick on a certain person. Does anyone know who Shaquille O'Neal is?
Yeah.
Okay. What's really hard for me is he was a Laker, and I'm a Boston Celtics fan. Because they happened to be the first team I ever watched in the 80s when I was a little kid, and I got into basketball, and Larry Bird made me feel like I had a chance to do something. Shaquille O'Neal famously did not shoot free throws really well. So, it doesn't even matter if you know who Shaquille O'Neal is. There's these things called free throws. So he just goes to a line and he tries to get it in the hoop, yes? Let's say he had a 30% chance of getting a shot in, yes? If he takes 20 shots with the basketball, how many would you expect him to make?
30%. No.
30% of?
The 20.
So how many would you expect him to make? 6. You guys with me?
Right.
Isn't this a binomial situation? Because what's P? 30%. What's Q?
20. Wait, round?
P is 0.3, 30%. Q is
Oh.
How would you
70%, 0.7.
How would you write that?
You ready? So what I just identify this as? What letter?
P.
P, because that's a success, yes? So we just did 30% of 20, yes? You write it this way just to be weird. That would be 20 times 0.3, is that cool? Which is 6, yes? You want to see a neat thing? Move that over once, move that over once, 2 times 3 is 6. You see that on the stupid Facebooks or the TikToks or whatever, they go, why was I never told? Shut up. If I multiply, this is 2 times 10 times 0.3, so I can just take the 10 and add and multiply it to this guy, I can move decimals around within a problem. You all have calculators, so it almost doesn't matter. So help me out. What's this, the letter for this in this situation?
E.
No, the letter for 20.
Oh.
N. What's this?
F. Oh, no. P.
P. You with me?
Yeah.
Okay. And what do you think, if that's the expected number of shots that we think he's gonna make, do you see how that's another word for the average number of shots he would make?
Right.
So that is the formula for the mean. This is the formula for the mean for a binomial distribution.
So it's like, for this one, like the 14 or 15.2 out of 44, you find out what that number is.
So looking back, and by the way, real quick, is everybody cool with this physical situation? I mean, anytime, if I said 11% of people are left-handed and I pick 500 people, how many people would you expect to be left-handed? 11% of 500, right? N times P. And it's something I forgot to say earlier. Do you guys remember this formula from before?
Yes.
This is just a complete coincidence. What do the first 3 letters look like in the formula? No, what's the first 3 letters look like in the formula?
E. X.
EXP, expected value. So the mean is also called the expected value. That's just coincidence, but it's kind of nifty. And I forgot to say that before. So coming back here. Yes.
I'm sorry, real quick. So the
Oh, I forgot something else.
it was called mean for binomial. What was it?
Yeah, it's just the mean for the binomial. So this is a binomial distribution,
Okay.
and this is the mean for the binomial distribution. So what did I tell you guys when we left chapter 2 and we got to 3 and 4? I said, I'm going to give you several ways. I'm going to give you data in different ways. What 2 things do we always want to be able to calculate? The mean? Standard deviation. So the standard deviation formula is here. The explanation for this would involve some calculus. So I'm not going to show you. This one is silly easy. This one you guys came up with and then we wrote the formula down. That one a little bit trickier. Because would you all agree that finding standard deviation is worse than mean almost always? So the formula is a little worse. But these are still the best ways to find the mean and the standard deviation. I don't have to make a table. I just need to multiply and shit stuff, right? So in this case, what was n? In this case, 44. And what was p?
0.152.
0.152. Cool. And I just got to multiply those.
6.688.
6 point.
688.
Sounds familiar? So out of any group of 44 San Diegans, I would expect about 7, right? So I don't want to chop anybody up. So I'd expect about 7 smokers.
So would you round, yeah?
Yeah, especially when we're talking about whole numbers of people. Now listen, when you, no. When you write the mean down, 6.688.
Right.
If I said interpret that, then you could say I would expect around 7. Right? Because again, I don't want to, 1, 2, 3, 4, 5, 6, you come here, chop. No, don't do that. You are now 0.688. No. Standard deviation, what would I throw in there?
P?
Square root of 44 times P times Q, and then I just got to throw that in the old calculator.
Oh, that's not.
Really silly side note. Didn't we already do n times P?
Yeah.
So when you're doing these problems, this is really silly. This almost doesn't matter. But if I do n times P, I can then do the square root of that times Q, because that is already n times P. Does it really matter? No. But I just want to show. So I get this. So if you do it all the way out, you should get the same number. Yes? So let me see if I do square root of 44 times 0.152 times 0.848, I get the same number.
You don't round this, right?
How much do you round it?
To the fourth, so never mind.
Well, to the third. So if you guys wanted to, remember I said standard deviation has to be at least 3 decimal places. So you can just make it 4, so it makes it easier to remember. That's fine. Yes?
Yeah.
Okay. So from this, we can define kind of an initial attempt at what unusual means. So very quickly, can you guys tell me, if I flip a coin 500 times, number 1, what's going on with my life? Where I'm doing this. But number 2, how many heads would you expect if it was a fair coin? 250? Yes? You guys with me? And now you know how they got that. What's the probability you get a head? 50%. What's n? 500. N times p? 250. So the average number of heads, if somebody flips a coin 500 times, would be 250. If I got 248, does that mean the coin is weighted? No, because you have a sense in your head. You have a sense of how far from 250. What if I got 240 heads? Is that still okay? Is that not evidence that it's weighted? Do you guys understand my question? If it's a nice, not weighted, normal penny, and I flip it 500 times, I should get around 250, yes? What is a round is doing a lot of heavy lifting? With 240 heads, does that feel like it would be okay?
Yeah.
What about 200 heads?
No.
See how that somewhere between 240 and 200, there's a line that was crossed.
Right.
So what we're about to do is our first attempt, and the most general definition for unusual in statistics is 2 standard deviations away. So we're going to do something that feels very familiar, but I'm going to use it to interpret something different. So if I ever ask you, would this be unusual? You put the mean in the middle. But now I'm going to go up 2 steps and down 2 steps. If it was a normal distribution, what percentage of the data would I catch if I did that?
68? No.
That's 1. If I go 2 steps out, 95. Yes? 95% of the data would be in there if it was normal. What percentage would be outside of there then?
5%.
Wouldn't you say something that has a 5% chance of happening would be unusual to see it happen?
Right.
Doesn't that feel right? So that's sort of, to be really honest, we just decided to define unusual like that. It's 5% chance. We're going to call that unusual. You guys kind of with me? Later this semester, we'll see if I'm in a nuclear power plant and the little needle starts to move towards the yellow. I'm not going to sit there and go, oh, sorry, wait till it's like almost to the right. Yeah, okay. I'm going to get that. I'm going to define unusual to be like 4, like 1 standard deviation away. Yes? I'm not going to wait for that sucker to get into the yellow. Yes? I don't want to attract Godzilla and all this shit happen. Okay. I like it. So, how do I construct these numbers then? What is 2 standard deviations up?
9.069. Oh, no. 11.
Yes, that's better. 11.45.
45.
Okay, sounds about right.
Minus.
And then if you do 2 down, is everybody with me? We've done this kind of thing before, but we normally only did 1 up and 1 down. Now we're just doing 2 up and 2 down.
1926.
Do it again.
1.926.
Okay. So what I've just established is a range for what I would expect to happen, the usual things that should happen. So if I found 15, if I took a group of 44 people and I found 15 of them smoke, would that group of people be unusual somehow?
Yes.
Because it's well above
2 standard deviations.
the highest usual value I would expect, yes?
Right.
You guys, do you guys know the name Aaron Brockovich?
Yes.
There's a movie.
Yeah.
So living in California, we should really know about this. Kelsey knows Aaron Brockovich really well. It's like, I'm better, I know her, we hang out. You guys, so the whole thing she did was she championed looking into contaminated water that was causing communities to have higher rates of cancer. So, is it possible that a group of people could just randomly have higher rates of cancer? Yes.
Yeah.
What she found, and what was already there and was being discounted, was evidence that their rates of cancer were higher, which should have been prompted an investigation, and they just didn't. Because, of course, that would cost money.
Right.
And they're a corporation, they don't want to do that. So she had to fight for them. She had to show evidence that yes, it was contamination. But the first level of analysis is that's outside the realm of usual. Let's go take a look. You guys kind of with me? Is it possible that they go take a look and nothing's wrong? They just happen to get cancer at a higher rate? Yes, that happens. That happens. But should we just not go investigate and go, that's probably one of those times, It's probably one of those times. Go ahead, swim in the shit. You guys kind of with me? Yep. So this is kind of like a first level analysis to see if we should go take a look at what's going on. Okay. By the way, for the coin thing, if I flip a coin 500 times, what's the probability I get a head? 50%, good. So that's just to kind of reaffirm this. I would expect to get 250 heads, yes?
Yep.
What's the standard deviation on that? So that would be in the square root of, that would be about 11 point something, I think. Yeah, 11.180. So what would be an unusual number of heads? Let's see. Put 250 in the middle. Go up 2 of those, and that's gonna be about 272.36. Go down 2 of those. Are you guys, I'm doing this a little quickly, but you guys kinda with me?
Yeah.
Go up 2 steps there, and if we go down 2 steps, that would be 228, I think, 227 point, it doesn't really matter that much, Jeff. 82. No, 0.64. Okay. Yes. Okay. So earlier, I asked you if 240 was unusual. And you're like, no. I asked you if 200 was unusual, and basically everybody said, yeah. Now we see by the official definition we have so far, 227.64 is where unusual would start. So if I flip a coin 500 times and get 226 heads, that is officially evidence that it's been tampered with. Does that mean it's been tampered with? No. Is it possible I flip a coin 500 times and I get nothing but heads and the coin is fine?
Yeah.
Is it possible?
Yeah.
Is it likely?
No.
Hell no. Yes?
Yes.
Okay. So we see this with like DNA tests in court cases. The really weird thing with those DNA tests is they have this high probability of identifying a person, but that doesn't mean that they always do. It's just that when you have that in conjunction with other evidence, that you're like, okay. You with me? Okay. So in terms of formulas for finding the mean and the standard deviation, the binomial distribution has 2 of the best. NP and the square root of NPQ, that's the best. I don't have to make a table, I just have to plug stuff in. You guys with me?
Mm-hmm.
So earlier that problem where we had, yeah. No, I can't remember now. So if I had, yeah, here it is, 66 people. Remember earlier we did this problem? 66 people. 66 people. And probably, there was left-handed was 11%, and the probably right, not left-handed was 89%. What would I expect? How many would I expect to be left-handed?
66.
Yeah, 66 times 0.11. 7.26, I like it. So if I have 66 people coming to a workshop, if I put out 8 left-handed desks, it's not terrible. That's more than I would expect, right? But couldn't more than that show up?
Yes.
So that's why I go the extra step and I look at a standard deviation. What would the standard deviation be? Let me see, 0.9, 6.3, 2. Somebody save me from myself. I think it's 2.5. What is it?
2.542.
Kick yes! 2.542. 2? Okay.
Oh yeah, 1.
Oh yeah, you're good, you're good. 2.542, okay. So now I can kind of like, if I go up 2 steps, real quick, is everybody with me? You guys agree what I just said? If I expect about 7.26, if I put 8 chairs out, that's a good kind of approach. Even better would be if I add 2 steps and I put that many seats out, it's really unlikely that I didn't put enough seats out. Does that make sense?
Yeah.
Yes.
So this is getting closer to what companies in real life do. How many seats on the plane? Did we overbook? They do this kind of analysis, right?
Yep.
So what would that be? That would be roughly 5.084. So that would be 12.344. So if I put like 12 or 13 left-handed seats out, I should not have a problem, more than likely. All right, is everybody with me on that? Okay, so this is, we're getting, day one you learned shit that would help you in the real world. But this is getting really close to what more detailed analysis leads you to. Just to kind of cover your bases. right? Okay. I like it. So, that's the binomial probability distribution. How do you identify that kind of problem? Does the problem say a total number of things or people? Does the problem give you a probability of something, and there's a chance that it was the opposite of that thing, right? So if I said I roll a die 80 times, what's the probability I get exactly 3 5s? You can identify the probability of getting a 5. They're probably not getting a 5. They gave me a total number. They asked me for a number of successes. There's a certain template for this kind of problem. Because in any math class, what's the hardest thing? Knowing when to do what. If you really think about it, every single math class, the hardest thing is knowing when to do what. Yes? A lot of times students kind of get the processes down pretty well, but they're just not like, when the hell do I do this thing? Yes? Okay. So last little bit for today, I'm going to let us out a little early. Seems to be my MO here. I would say don't get used to it, but well, just don't get used to it. Who knows? I might keep you full time sometime. A little peek into chapter 5. So what we just did was all 4-3. Has any of you? All right, let me ask you this way: do any of you have no idea what I mean when I say darts, dartboard? Does everybody understand what darts and a dartboard is? Have any of you guys actually ever thrown darts? Yes. Has any of you thrown dart into somebody's head?
Yeah.
Man, my parents put up a dartboard, let us use it without them around. And sure enough, my little brother ended up with a dart. All right, there we go. Fantastic. Doesn't let me forget about it. Why would it be impressive for somebody to get the dart in the bullseye several times in a row? Why exactly would that be impressive?
It's hard to do.
Why? Small what?
Probability.
Small target, small, I think I heard the right,
Probability.
starts with an A.
Markers.
Small area, yes? So it would be less impressive, it would still be impressive if I got in this section several times, but it would be less impressive than if I got in this section, yes? Okay, is everybody kind of with me? So even if you've never thrown a dart in your entire life, you understand the basic premise, you try to throw the sucker, and you try to get it on the board. If you play actual darts, the bullseye is not immediately the most important thing because you're talking about score, blah, 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 blah. Okay. But if somebody wanted to impress me, show me they could really throw darts well, I would want them to throw in the bullseye like 7 out of 10 times or whatever. You can each set your own baseline. You guys kind of with me? Yeah. Okay. The reason that's impressive, now it would be equally impressive if I just draw a similar sized circle anywhere on the damn board and they get it in that circle. Yes? It has nothing to do with where it is. It has everything to do with how much area I'm giving them. So it seems that the area of the spot I'm focusing on is related to the probability. So if I was just blindly throwing darts and I only counted the ones that actually hit the board, the area of the section would be the probability that I would get it in that section, yes? Now, if somebody's really skilled with darts, they beat the odds by getting it in a certain area more than they should. And that would be evidence that they have actually trained, that they actually know what the hell they're doing, yes? Which I obviously don't. If you play darts, I'm not really doing it here. Wondering. So if this area, if it was 10% of the total area, what would the probability of getting it in there be? If you just throw the dart randomly. If that area is 10% of the total dartboard area, what's the probability that I would randomly get a bullseye? 10%. 10% of the time I would get the bullseye, yes? It's related to if 10% of you guys liked lima beans, and I pick one of you, what's the probability I pick somebody who likes lima beans? 10% is exactly the same kind of idea, yes? So, what's the probability? Now this is a silly question. If I only count the ones that hit the dartboard, what's the probability that they throw darts and I count somebody hits the dartboard? 100%, yes. So the whole board is 100% chance. And then each little section would be whatever percent based on how big it is. Yes. So this section here might be like 18% or something, or 20% or something, right? It's a little bit bigger, yes? Okay. So that's why it would be really, if I threw one dart and got it in the bullseye, is that evidence that I'm really good? No. 10% chance, 1 out of 10, you could have gotten lucky. Throw it again, and I'm like, pop, 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 and you're like, all right, dude. And then, pop, 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 oh shit, yeah, no, right? You guys got it with me? Yeah. Okay. So how does this relate to what we have to do? There are many situations in real life where the probability distribution looks like a big rectangle, has the same height. Let me ask you this question. Every problem we did in chapter 4, think back to chapter 4, the problems we just did earlier where I was counting how many people were left-handed, is that a discrete or a continuous distribution?
Discrete.
Yeah, because could I have 2.73 people left-handed? No. So everything in chapter 4 is discrete. A dartboard, isn't there basically almost an infinite number of places that it can stick into the circle? If you really get down to it?
Yeah,
Okay.
continuous.
What about, catching a bus? Let's say that we're in a city where the buses actually run perfectly on schedule, right? We're maybe in Germany. Italy, I went to Italy, and the train was an hour and a half late. And so where's the train? He's like, hey, it's fine. Got there 2 hours, perfectly on time. Waited. Germany, train's 2 seconds late, everybody's freaking out. Okay. Very interesting. Let's say I'm in a place more like Germany, and the buses just run perfectly on schedule. They come every 15 minutes. You have to catch the bus. What is the best situation? Right when you get to the bus stop, it's there. So how long did you have to wait in that case? 0 minutes, yes? What is the worst situation? It just is leaving right when you come around the shit. How long will we have to wait then?
15 minutes.
15 minutes. You with me?
Yeah.
So if you get there and you don't see the bus, do you have any clue how long the last one left?
Yeah.
No. So you could be anywhere from 0 to 15 minutes. Equal probability all the way across the board. So here's what that would look like. Now, I want to remind you guys, why was it easy to tell the probability for this? Because I made the whole thing equal to 100% or 1, yes? So then the area being 10% of the whole thing meant the probability was 10%. I want to make the height of this such that the area of this is 1. What is the area of any rectangle? Length times width. What is the length of this one? 15. So I want the width, or the height, because I stood this thing up. Is that cool? I want the height to be such that when I multiply 15 by it, I get 1. What number do you multiply 15 by and get 1? And I want the exact number, not an approximation.
Sorry.
I want the exact number, not an approximation. You'd have to keep going for the rest of your life and then have your sons or your daughters or whatever continue in your study. Because that never ends, yes? So real quick. What's the mathematical idea of taking a number, multiplying, and getting 1? That's the multiplicative inverse. What's another name for the multiplicative inverse? Multiplicative inverse. Reciprocal. What's the reciprocal of 15? 1 over 15, that's the height. Was it 15 because that number is 15? No. It's because this length is 15, yes? Does every one of these have to start at 0? No. So it depends on what this length is. Do you all agree with me that this is this situation just in a big block. The total area is 1, yes?
Yes.
So what about if I get there, I don't see the bus? What's the probability I have to wait between 6 and 8 minutes? Can you draw that in your picture? Figure out roughly where 6 and 8 are, yes? Doesn't have to be perfect, so 6, 8. Doesn't that make an area?
Yeah.
Just like me asking you, what's the probability somebody gets that in the bullseye? If they're just throwing random. It's the area of that piece. So what's the probability I end up between 6 and 8? It's the area of that rectangle. How wide is that rectangle I'm looking at? 2. And how tall is it?
115.
So what's the area? 2/15. And now you can give that to me in a 4 decimal rounded way, yes? What is 2 divided by 15? It's 0.127? What is it? 0.13? 0.13? 133? 3? Okay. That's almost too nice to believe. This is chapter 5. This is all of chapter 5. Is if I have a uniform, we call it a when I say the word uniform, what do you guys think of? What's the first thing that comes when I say uniform? Sorry, you think of school?
Yeah.
All right, why? Did you have to wear a uniform to school? Not to, okay. What does that mean? Everybody
It's all together.
had the exact same thing, correct? So a uniform probability distribution is one where every event has the exact same probability. That's why we call it a uniform probability. So if I say I have a uniform probability from 1 to 9, you're going to make a rectangle from 1 to 9. How tall will that be? Well, how long is this 1 to 9? How long is it from 1 to 9? 8. So what will the height be? 1 over 8. And then you can answer any question I ask you. You just got to draw the little triangle that represents the question I'm asking you. Just like finding the little bullseye and figure out what the area of that is. Okay. Maybe. So real quick, last one. If I have 1 to 9, let's say this is the time it takes me to find my keys. Is at least 1 minute, up to 9 minutes, yes? And uniform probability, so it never takes me less than a minute. Okay. I'm not sure why the crowd went wild in that. Go, Jeff! So what was the height again for this?
1 over 9?
No.
Oh, 1 over 8.
How long is this? Yes, so be careful. Don't just focus on the number. The first one I did started at 0. And that's why it was just the last number, because 15 minus 0 is 15. 9 minus 1 is 8. Now the area of this is 1, correct? So what is the probability that it takes me more than 5 minutes? You're going to find what here? 5. So 5 is maybe right there. Which way am I going to shade? Up. So how do I find the probability that I just translated into finding the area of what I just shaded?
Right.
So what I just shaded, how wide is it?
It's 3. Oh no, sorry.
4. And how tall is it?
1/8.
1/8. So it would take me 50% of the time, it would take me more than 5 minutes. Okay, so that's chapter 5. There's definitely more to it. What have I haven't shown you how to find the mean and the standard deviation in the situation. So I'm gonna let us out. Next time we'll get deeper into uniform probability distribution stuff. Cool. Anybody not get their quiz back? Okay.
Just go to the lines here.
right, guys. Have a good weekend. Don't forget your IDs. Dear God. Please don't forget your IDs. Oh, sweet.
This is a D.
Yeah. So you can get 5 points back if you do corrections. Good job.
I normally did really bad, like math anxiety, so I'm surprised, not surprised, but I'm really glad I'm doing well in this class.
Yeah, you're doing good. Yeah. Keep it up. Oh, sweet.
I'm running out of cool stuff to give you, so I'm gonna bring you my immigration papers next week.
Oh, okay, okay. I'll take that.